this works. Okay, we are now live. So, oh wow, 16 people. People are excited for this topic. So, hey everyone, today we're having our guest lecture from Lorraine on Commonsense. And before we start, I just wanted to let you know that we have an extra credit assignment. Lorraine would really appreciate some feedback on her lecture, the pacing, the content, how useful you thought it was, and whether you had the right background to understand everything. So there's a feedback form in the LinkedIn Piazza and also on the website, which you can click and complete, write some comments about the lecture. And if you do that by next Monday, we'll give you a small amount of extra credit. So this will be on top of your existing current extra credit assignment. Other than that, yeah, I mean, obviously your only remaining deadline other than the quiz is the final project report, so make sure you're working on that. And finally, for this lecture, if you have any questions, I'll be monitoring the chat window. So whenever you have a question, just write it in there as normal, and I will ask it to Lorraine. So, okay, with that out of the way, why don't you go ahead with the lecture, Lorraine?
Yeah. Thanks so much for the introduction, Mohit, and thanks for having me here. I'm really excited to be here and giving this lecture, giving this guest lecture. You can stop me at any time during the lecture with questions if there is any. So you don't have to save them up. So let's get started. I'm Lorraine, a fifth-year PhD student working with Andrew McCollum at ESO. And my research interest lies mainly around common sense reasoning, ranging from learning a good representation that has the correct inductive bias towards representing a certain kind of common sense knowledge, to how can we design benchmark data set to evaluate models with certain kind of common sense knowledge. So first of all, what do we mean here by saying common sense knowledge? One type of knowledge as shown in this example is, it is obvious for us to know that a lake will be divided into two lakes when the water level is full. So a 5-year-old would probably know this. And some other things a 5-year-old would know is when they're playing this kind of brick toys, if you don't place it correctly, then the brick is going to fall down. So then what do we mean here by common sense knowledge? It's a sound practical judgment with concerning everyday matters, and it's about someone's basic ability to perceive, understand, or judge certain situations. And it is also shared commonly to nearly all the people. So what are we defining here is apparently we're not referring to everyone in the world, because if it's a child who grows up in Amazon jungle who would never play this kind of fancy toys ever. So sadly, with that in mind, we're not referring to every single person in the world, but instead we're referring to nearly all people. We're targeting this group of people. And then specifically in NLP, it's actually everywhere. For example, in machine translation, when we try to translate an English sentence to a German sentence, the software or the tool needs to understand what the word working mean here, because there is different two words for working in German. Either it means a labor or profession, such as the electrician is working, or another meaning would be the telephone is working, meaning it's functional properly. So those are actually different two words. The software needs to know what this English working actually meaning here in order to get the correct translation in German. And furthermore, in smart home assistant like Google Home, this is a real example I saw someone posted on Twitter the other day. This person is not able to find their phone, so they ask for help. He said, "Hey, Google, can you call me, please?" And Google said, "You sure?" This person, "Yes, I'm sure." And then Google said, "Okay, yeah, I will call you, please, from now on." So this is apparently a misunderstanding. And but from our point of view, it's actually really easy to understand this, but it's kind of just a really hard task for machine to do this. So since it is so important, there must be previous attempts that tries to solve it. There has been big effort has been pushed in the 70s or 80s by researchers of using logical formulation to represent common sense knowledge. And the Turing Award winner John McCarthy is one of the frontiers that formalized common sense as a logical-based problem. He published several papers using logic system to represent common sense knowledge. In one of his first papers, this paper called Program with Common Sense. This paper is especially important because it was probably the first paper on logical AI back in 1959. And it is also the first paper pointing out common sense reasoning as the key ability for AI system to have. So in this paper, he said, in order for a program to be capable of learning something, it must first be able to be capable of being told it. That's why we need this logical formulation to tell the machine that this is the kind of knowledge you have to know. So in this paper, he proposed something called advice taker, which represents knowledge in the following way. It's almost like a triple, like I at desk at home. It's very similar to the knowledge-based representation right now, but I think it's very different in a number of different ways. But this is one of the first attempts to representing common sense knowledge using logical formulations. And after that, there has been many logical systems being applied in the domain of common sense. And this is probably an incomplete list of all these different logic systems. But just to give you an idea of how diverse these logic systems are, with propositional logic as a start, and you can do different modifications on top of that. That gives you first order logic or modal logic. These are all deductive reasoning logics. And apart from this, there are also plausible reasoning logics, including non-monotonic logic, probabilistic logic, or fuzzy logic. With this many different logic systems have been proposed or have been tried, there was some progress with modeling common sense knowledge back in the days. But the overall story is it did not end up well. As said by Yejing Chu, who is currently a professor in University of Washington and is one of the professors who is now actively working on common sense reasoning these days. She said in her PhD time, she was told not to speak of the word common sense, which is at around 2000, at the start of 2000, or sometimes like that. But she also concluded that the past failure of representing common sense knowledge is inconclusive, including the following reasons. But this is not an exhaustive list of the following reasons, but these reasons probably contribute to the failure of the common sense reasoning part. There are not enough computation powers, there was not GPUs available, and not so much data, and there's no tool called Mechanical Turk such that we can gather enough information from people to annotate this data for us. And also there's not as strong computation models, like there was neural networks, but due to the above two reasons, neural network actually was not working great. And also there is no ideal conceptualization or representations to represent this kind of knowledge. So with that in mind, I think we can have a brief outline of today's lecture. I've been talked about common sense knowledge, and we said there is not enough there is no correct representation. So the next part will be how can we learn the right representation? And we'll also introduce some common sense knowledge in whether there are common sense knowledge in pre-trained language models or not. And then finally, we'll talk about how to build benchmark data set for evaluation. So how can we learn the kind of representation, or what is the kind of right representation to represent certain type of knowledge? In NLP, we typically learn a vector representation of words, as in word2vec or like BERT representations. And this learned vectors showed word semantic similarity through this distance between words. As a result of that, similar words will get clustered together. As you can see here, there is an animal cluster and there is a furniture cluster. But if we look closer to rabbit and mammal, mammal is a much general concept, including lots of small concepts like rabbit. But this point representation cannot capture the size of the region referring to the word, where the size of the region represents the number of concepts can be expressed using this word. And moreover, rabbit is a mammal, but mammal is not rabbit. The kind of naive score function like dot product, cosine similarity between vectors cannot capture these asymmetric relationships. So our lab proposed in 2014 to expand this point representation into a Gaussian distribution. So the representation will now become region-based. It is also asymmetric because the rabbit Gaussian, as we can see here, will be inside of the mammal Gaussian to refer that rabbit is a mammal, but not vice versa. Furthermore, it can express the disjointness between concepts, as there are no region overlap between deer and rabbit if we give certain threshold to the Gaussian distribution. But one drawback of this representation is that they're not closed under intersection. The intersection between two Gaussians are not necessarily a Gaussian distribution, which makes the model is really hard to train and the computation really hard as well.
Lorraine, can I interrupt really quick?
Sure.
There's one question about your example that you showed a while back with the brick. I guess there's a comment. Is this really common sense understanding or more observation-based understanding of the physics of our world, since there are programs or graphics engines, stuff like that, that have encoded these kinds of physics-based behaviors already into their system?
Yeah, this is a great question. And I think by saying common sense reasoning, it's actually a big umbrella term that involves a lot of different types. And physical common sense is definitely one type of them. One thing would fall down naturally, that's the gravity would tell you that. That's definitely one type of common sense. And there has been active areas in vision or video working on this as well.
Do you, I guess there's a follow-up question from the same person. Have there been any methods in NLP for common sense reasoning that explicitly encode this kind of information about physical behavior, physics, etc., into the model?
Yeah, that's a great question, follow-up question, because there is definitely benchmark data set that targeting this kind of physical common question answering task, which I would introduce later. So I believe then the models who get really good scores on that data set will have a way of encoding this physical knowledge into the model in order to perform well for that data set.
Cool.
Yeah. So yeah, back to our representation learning, we have this Gaussian representation, and as we said, there is one drawback of this representation because they're not closed under intersection. And then after that, in 2015, another representation comes out, cone representation, mitigate this problem by representing each concept using a cone, referring to the region towards infinity. And now it is closed under intersection because the intersection between two cones, it's still a cone. And in 2017, there's another paper extend this representation to a probabilistic model by constraining the space into a unit space and assigning less density to each cone as the cone extend to infinity.
Lorraine, sorry to interrupt again. There's a clarification question on the Gaussian embeddings. Why are these regions called Gaussian? I'm familiar with the term in probability distributions data sets, but I'm not sure what it means in the context of regions. That's the question.
Great. Sorry for not making it super clear. But in this representation here, we actually represent each concept using a Gaussian distribution. So If you want to make it super specific, it's two vectors. One vector represents the mean, and the other vector represents the variance of this distribution. So it's literally a Gaussian distribution for each word. These are great questions. Feel free to ask more. And where were we? We have this probabilistic notion of this Cohen embedding grid. So yeah, the probability, now we have this probability Cohen embedding representation, and the probability of each concept will equals to the volume of the cone integrated under this exponential function. But each cone will still extend to infinity. An immediate concern is that we cannot make rabbit and deer, in this case, disjoint anymore. And however, the situation will get even worse. Conditioned on one or more variables will always increase the probability. For example, here, assume the probability of being a rabbit is like 12.12, and we want to get the probability of rabbit conditioned on deer. If you want to guess, the probability of rabbit conditioned on deer should be 0, because if you're a deer, there's no way you can be a rabbit. But for this model, after conditioning on deer, the universe of this calculation becomes the deer box, which will give us, like, for example, 0.4 probability, conditional probability, which doesn't make sense at all. This is a very bad thing for a probabilistic model. So following up this work, in 2018, we propose, try to fix this problem in a natural way by giving an upper bound to Cohen embedding. So, by representing each concept using axis-aligned hyperrectangulars, boxes, in other words, boxes. And this is a 2D illustration. In this representation, it is region-based, and it can represent asymmetric relationships because one can inside of another to represent is asymmetric. And they're also disjoint because they're also closed on the intersection because the intersection of two boxes will still be a box. More importantly, disjoint concepts like rabbit and deer can be represented. Now the probability of rabbit given deer should be 0.
So I think you addressed this question mostly in what you just said, but if you go back to that previous slide, there's a question on why is it necessary for these concepts to be represented such that the properties like region, asymmetry, disjointness, etc., are held? Like, why are those properties important in this kind of representation?
Good question. So region, because we want, as we said, the vector representations, mammal and the rabbit will have the same representation. There is no notion of how general this concept is. So we kind of want this region representation to represent how general this concept is, and how can I using this word to refer more general things, or I can only use this word to refer very specific stuff. So that's why we want region. And asymmetric is this kind of Aza relations. Rabbit is a mammal. We want to have rabbit is a mammal, but mammal is not rabbit. This relationship between these two words are not symmetric. And disjointness, as we said, because that probabilistic model will not give us, if you condition on one thing, it's the probability of deer given rabbit will become bigger, which means something can both become a rabbit and a deer. It's a very unintuitive thing. I don't think that's common sense. And why they're closed? Why do we want closed under intersection? Because that makes the calculation extremely easy. Because in the end, we want to get the representation of these things.
So there are two more questions. One regarding closed under intersection. Could you please explain what that means?
Closed under intersection means if we take two of these regions and we take the intersection of these two regions, are they still the same unit representation you was working on before? Like boxes, you take the intersection of two boxes, it's still a box. Cones, you take the intersection of two cones, it's still a cone. That's what we mean by closed under intersection.
Great. And the second question is, Is the region-based representation similar to doing something like a hypernym discovery on vector space?
That's a great question. That's how we get motivated. And this kind of region representation should work extremely well for hierarchical relations, which is hypernames.
Great.
Yeah, those are all great questions. And now we have this box representation, and it can, it can represent disjoint concept. That's why we want this disjointness. We don't want anything, give me a probability of rabbit given deer. We don't want it to be more than 0. And as we said, this is good for common sense representation. What can we do with this? We also try to use this box model to model common sense. And as a first step, we train the LSTM to take arbitrary short phrase as input and then output a box. And this is an illustration of boxes trained on an entailment task. And as shown in this cherry-picked example, if something is B on bench, it's likely you're sitting down. But if you sit down, there is much less probability of you are sitting down on a bench because there are lots of other things you can sit down. In addition, if we add this third box of man relax, it is going to intersect with B on bench and sitting down by or a small portion, but it's going to be a big box because there are lots of other different ways for a person to get relaxed. To give you more intuition of how this model is getting trained, I want to show you this video of training a 2D boxes on 7 movies. Even though movies are not common sense knowledge, but boxes is like more general than only representing common sense knowledge. It's a representation can be viewed as a probabilistic model that can capture any kind of joint distribution with for binary random variables. So the goal here is we want to say similar movies should end up having a similar box representation, and the size of the boxes represent how many people have rated this movie in a relatively high score. As you can see, all the boxes are initialized randomly. After a while of training, we can see similar movies get clustered together. Lion King and Aladdin, they're overlapping with each other a lot. And Forrest Gump is a pretty big box because presumably a lot of people just like this movie and rated pretty high in a high score. Also, Rear Window, North by Northwest are both movies directed by Hitchcock. They probably have the same group of audience as well. And also the Lord of the Rings series.
There's a question. Could you clarify again how the box representation is defined mathematically? Is it a matrix or a bunch of coordinates? What is it?
Great. It's a bunch of coordinates because if you can see here, we actually represent the boxes using a lower left coordinates and the upper right coordinates. So when you actually do the training, it's 2 vectors. But it has certain like geometric constraints, like the upper right has to be bigger than the lower left. So that it won't violate this. You actually have a size of the boxes.
Great.
But there is training difficulties with this model. The current model, if one box is inside of another, and the goal of the training objective is to make them disjoint. One thing we cannot do, or it's really hard to do, is to deal with this kind of situation. Because imagine, no matter how you move this purple box, a blue box inside, the gradient of the intersections, the box's intersection size will not change. So as a result of that, the loss will not change. So you will get 0 gradient. And hard box training result will become like this. And this is just one case. Another case would be, what if 2 boxes are disjoint? And the goal is for them to intersect with each other. We're in the similar situation. No matter how you move these 2 boxes, the intersection doesn't change so that your training result will still probably look like this. There are lots of local minimums in this training objective. So as a follow-up, we proposed, this is a loss function of the original box paper. As you can see, there is this big drop, but if you're outside, it's all the same. If you're inside, it's all the same. The iClear paper in 2019, we tried to solve this boundary problem on the outside. And then in the NeurIPS paper, which is coming out in this year's NeurIPS, we represent boxes using a gumball distribution where we have gumball boxes. And now we just there is a smooth loss function everywhere. And these are like this very high level. And if you're interested, you can always contact me for more details of how do we do this gumball box and smooth box. But in general, the message we want to convey here is it's a good representation. And now it doesn't have this all this kind of training difficulties anymore. As we propose the different ways to represent common sense knowledge, let's look at a properly trained example. Same example as before, the probability of being deer. If you condition on different things, you will get different probabilities. Like not white, you will get a little bit higher. If it's an animal, it's gonna be much higher. And after you condition, if it's herbivore and if it's not white, not rabbit, is animal, is a herbivore, it's going to be pretty high probability that this thing is a deer. But the moment you change herbivore to not a herbivore, the probability becomes 0. And this ability of being able to answer queries with negated variables is kind of unique to geometric representations, because there is no way you can do it for vector representations unless you iterate through all the possibilities, and which is really expensive.
We have one more question. Mm-hmm. It seems that the intersection of boxes would have a higher possibility to be smaller in high dimension space. Is that right?
That's great. Yes, that's correct. And that can give us some like numeric instability when things become super small. So you have in the actual implementation, you have to use numeric stability functions to avoid this kind of problems.
Makes sense.
That's a word example, and this is a sentence example. We tried boxes as we showed before on sentences by using LSTM to output a box representation. And this is a data set we tried it on. It's a Flickr data set. It's an entailment data set containing image of 45 million of image captions. And after training on this, you can see the probabilities with one condition on another varies from 0.0 to 1.0. If you're conditioned on a blonde woman walking down the sidewalk, the probability of person walk is 1. And on the other hand, if you say conditioned on hold instrument, the probability of you being in the basement is pretty low. It's still probable, but it's a very low probability that you're actually in the basement. So we've talked about how can we learn certain kind of representation that have this certain inductive bias to represent hierarchical knowledge. And concurrently, vector representation have gained a lot of success by training on large corpus. So now we're going to talk about common sense knowledge in pre-trained language models. Before that, do we have any more questions about boxes? Happy to answer more.
I guess I will ask one of my own. So we've talked in this class for this whole semester mainly about self-supervised objective functions like language modeling or masked language modeling, things like that. Do you think there are any ways to devise self-supervised objective functions for these kinds of geometric representations that will also give you some of these properties that are, obviously desirable, but seems like you can only get currently by training on some sort of structured data?
Yeah, we get that question a lot by, yeah, your representation seems great, but what does it perform when you apply it to downstream tasks? Like, can you do language modeling with it?
Mm-hmm.
And the current answer is we're still exploring, because for vectors, you can define the addition and multiplication with vectors pretty easily, which is actually the core of neural networks and the core of how all of those language modelings. But in boxes, it's actually hard to define those operations. What do you mean if you do addition with two boxes and multiplication with two boxes? So my advisor, Andrew, is super interested in this, and he's been pushing us for working on deep boxes for a long time. So, but it's not an easy problem, so we're still working on that.
Great.
Yeah. Now things, it's a great transition. You've been talked about a lot about language models. Does those language models have common sense knowledge or not? That's the next question we're going to answer. We often see a lot of news headlines like, a robot wrote this entire article. Are you scared yet, human? Which probably means, yeah, the language models works really good. And this misleading news concept are giving us a lot of, it's almost giving me heart attack. Like, oh my God, my research is just done. Like, there's no need for common sense reasoning at all. So luckily, researchers have the same question as me as well. So there are lots of work trying to answer this question. Does the pre-trained language model already capture common sense knowledge? One common approach is that people will using existing common sense knowledge base to probe language models. The way people do it is to take an existing common sense knowledge base, change that into a natural language template, and pass this template to a language model, using language models to do query or scoring on your transformed natural language. There are two papers from these two groups almost concurrently at EMOP last year. And they take the similar approach by both taking knowledge base and language models to do its job. This is some details. Most of them using this knowledge base called ConceptNet, which is probably the most user-friendly common sense knowledge base dataset, common sense knowledge base out there. And also there are Wikidata or doing some mining from Wikipedia, but this is a common sense knowledge base they use. They use handcrafted rules to transform triple representation to a natural language. They evaluate on different models, Elmo or BERT. And here are the conclusions. The Llama paper said BERT performs well, but almost all the models performs really poorly in many-to-many relations. And then the other paper said, this kind of probing performs much worse than supervised method if you try to do a classification task on ConceptNet. But it is more likely to generalize to different domains. As we said, those two papers are all using handcrafted templates to transform this relation triple to a natural language. So does this prompt and the sentence you give it to the language model matter? Does this matter? The answer is yes, it matters. In this year's EMOP, there is this paper called Auto Prompt, propose a way to generate prompt using automatic method. The intuition is to generate prompt tokens such that the token can make the biggest effect when predicting the label. And the effect is measured by gradient. So this is also called gradient guided prompt generation. One thing to notice here is that this automatic way of generating prompt, probably the sentence generated by this is not guaranteed to be grammatical, but it can make the most effect on the model predictions, as shown in the result here. For the same Llama probing as we did before, the Llama paper only gets MR score on 40, but this auto prompt gets up to 53 MR score. So that's saying the kind of sentences you pass into models definitely matters. So keep in mind of that when you try to do some probing to language models. Another line of research that people have been using to probing language model with common sense knowledge is to check the properties of the concept.
Wait, sorry, one second. One question I have with that is, can you really say that a language model encodes some fact if it only produces it when you probe it with a one particular context and it outputs something completely different with other like different paraphrases of that? What does that mean exactly?
Yeah, I'm not sure whether like the case you said before, you just mentioned it's a pretty extreme case.
Uh-huh.
My guess would be there are certain group of ways of doing formalize the sentence such that it will predict a reasonable answer. I won't say there will be very different predictions,
I see.
but it's really hard to say. I think that's something we all need to keep in mind of. Like, it's really hard to say this model has common sense.
Yeah.
Because that's a really hard
Right.
treatment you're trying to make there. So I think we can all just do a little bit of careful study on that topic. And yeah, so this is another line of research people have been using is to check the properties of concepts. They tries to ask two questions here. Do pre-trained language model correctly distinguish concepts associated with a given set of properties? And also, can a pre-trained language model be used to list the properties associated with a given concept? The first question, can the language model distinguish concepts associated with given properties? They designed this task by giving the model a set of properties and then let the model predict which concept having this property. So for example, here, blank has fur. You would have lots of different options, a lion, a bear, a cat, dog, they all has fur. As you gradually add properties to this prompt, has fur is big and has claws. Now you're supposed to like rule out some of the concepts. And as you grow bigger, the list grows bigger. Is an animal, it is brown, then you only probably left with this one single concept bear. For the answer of this question, in that paper, they said, the model generally get good performance and Roberta performs better than BERT. But there are some properties it's easier to distinguish than some other properties, like perceptual properties, which requires visual reasoning. And also, perceptual performs worse than non-perceptual properties. And also the highly ranked incorrect answers generated by the model is typically applied to a subset of properties. And seeing the model is not being like wrong by a large margin is getting some of the stuff correct, but not entirely correct. Now, here is the second question. If it can distinguish the properties, then can it list the properties associated with this given concept? For example, here we have bear, and everyone, if you give this to human, everyone knows that a bear has human response like fur, claws, teeth, paws, these things. And then Roberta said it has teeth, claws, eyes. In general, it has a low correlation with human illicit properties, but they're coherent and mostly verifiable by human, as we can see here. So I hope now based on the probing papers or the probing experiments we see before, the hypothesis might be there is some knowledge in the language model, but certainly not all of them. And then if there is some knowledge, can we trust the knowledge from the language models? The general answer is no, you should be careful with that, because there are these two papers saying take different aspects of what kind of wrong facts language models can generate. For example, here, Brock's wife is Hillary, which is not correct. And also, bird can talk but cannot fly. These two paper titles just said very clearly of what kind of knowledge, wrong knowledge is the model can generate. They're either distributionally related but incorrect, or they're syntactically similar, but also they're incorrect. So those are some probing works that tries to do to check whether there are common sense knowledge in the pre-trained language models or not. Following that, except for this kind of probing task, there should always be a benchmark data set for evaluation to tell us, are there standard benchmark data set to evaluate the model that contains common sense knowledge? A standard way of doing this is using a question answering data set. Besides that, you can also do natural language inference. As the example we showed before, a woman is walking along the sidewalk, can infer a person is walking. Or co-reference resolution, like John asked Alex, where is the library? He said, I don't know. Then where does, who is this he refers to in this example? And there are also many other ways of designing this benchmark data set, but these are some examples. Here I tried to list different types of common sense data set we have in this community. And this might be an incomplete list, but just give you a sense of how people have been trying to create such benchmark data. The first one is Hello Swag, and it's a multi-choice question answering problem, targeting at grounded common sense. For example, here, a woman is outside with a bucket and a dog. The dog is running around trying to avoid a bus. You are supposed to choose the correct answer from these 4 choices. She gets the dog wet and then run away again. C is the correct answer. And the best model performance currently, the model performance to human performance is only not enough, less than 2% difference. That's grounded common sense. There is this abductive NLI, takes the format of natural language inference, but still is a multi-choice selection problem. It's targeting abductive reasoning, and the difference is 3-pointed difference. Cosmos QA, targeting reading comprehensions with common sense knowledge, has around 2% difference. And physical IQA, as I mentioned, this is a common sense data set, target explicitly on naive physical reasonings. And the performance difference between best model and human is around not even 5%. And the social IQA, how would you, there is certain aspect people are expecting of when we talk to people. So this is about social common sense. Again, 5% of difference. And Winogrand, which is the co-reference resolution problem, as we talked before, even for this, it seems a really hard task. There is only 3 points of difference between human and the best performing models. And finally, there has been effort trying to combining vision and language together, this VCR, visual common sense reasoning. Even for this, there is only 2% of difference. So one thing you probably noticed already is the gap between models and human performance. They're all very low, but does that mean we actually solve this problem? I would strongly disagree with this argument, because if you look at this type of tasks, they're all multi-choice selections. You only need to select one correct choice from two to 4 candidate choices. But this is not really how we do common sense reasoning. If you ask a human what's the property of a bear, you're not supposed to select between, is it brown or is it red? You're not doing that, but instead you're coming up with this word brown or it's big, you're making the selection from all your word vocabularies, not just a selection between two choices. That means a more natural way of doing such evaluation is probably by generating answers, giving a question.
Quick question. Any evaluation data set of logic problems?
Yeah, I think there is. Not that I have listed here, but I think I can't remember the name of the data set. I can try to find it out later, but I think there definitely is.
I think there's also the synthetic baby data set from Facebook, which I don't know if we consider that a real data set or not, but if there were a real natural language version of that, that would be an example.
Yep. But I think there are, apart from baby, there are all different logical reasoning data set as well.
Yeah.
I just saw a paper reporting a new numbers on that data set, but I forgot to include them here. There's too many benchmark data sets now. So, but in general, we want to do generative evaluation instead of multi-choice selection. Why haven't people done it yet? Because it's a hard way to do it. There are multiple correct answers. And when you're trying to do this, the stream matching between two answers, your answer and the ground truth answer, might not be general enough to capture all the answers. And in addition, some answers is probably more common than the others. How can we capture this? As a first attempt to this, in EMLP, we proposed this data set called Protoqa, capture prototypical situations that with generative evaluation. Like name something that people usually do before they leave the house for work. There are so many different options you can answer. Like here we ask 100 people and 43 of them said shower, 30 of them said breakfast. And then there are also people saying goodbye, pray, getting dressed, locked door. So those are all available answers. And in this data set, we try to capture all of this. So our data set has multiple correct answers for each question. And for each answer, we have a score. In addition, we propose this generative evaluation that can evaluate multiple correct answers generated by the model. As we said, stream matching might not be good enough. So in the paper, we also proposed the word net matching, or you use the vectors, the distance between vectors to match the similarity between two words. And for this generative evaluation, we also try to reward model has the correct ranking of the answer list. You don't want the model have the same score if they output shower pre or pre-shower, because clearly the first one is preferred. We also reward model with a higher coverage of the answer list. So this is another of our work at EMLP tries to do this. How does the language models doing on this then? First of all, we test on question answering data, on question answered model. It's not doing great, mainly because this is really an open domain question answering, and we don't have ground truth supporting articles. We used distant supervised supporting articles, which can be really noisy. So that might contribute to why this QA model is not performing great. GPT-2 is definitely doing better than QA, and in order to make it fair for GPT-2 to do the job, we changed the prompt to name something that you would do to one thing you would do blah blah is. So yeah, GPT-2 performs a little bit better after fine tuning with our training data. GPT-2 performs much more better. But one thing I want to stress here is GPT-2 did not generalize after reading our training data. I think it means it more like GPT-2 is getting used to the task format. And the answer is probably already in there already. It's just without fine tuning, it's hard for GPT-2 to understand what you are looking for here. But still, all the models has a large gap compared to human performance, indicating this is a hard task. And as a summary of today's talk, I talked about common sense knowledge in general and its past failure of modeling using logical formulation to do such modeling, and also what kind of representations we can learn, in this case, box representations, to capture certain type of common sense knowledge, and also whether there are common sense knowledge in pre-trained language models, what kind of problems we can done and have been done. In the end, how can we generate a benchmark data set for evaluation of such common sense knowledge reasoning part? And that concludes my talk or teaching. And since I talked about some papers, I'd like to thank all my collaborators. And that's it.
Yay. Thanks, Lorraine. I don't see any new student questions, but I guess I will ask one to kind of relate this back to a previous lecture we had, where we discussed GPT-3 and also the Emily Bender and Kohler paper on whether a model can learn meaning from just form. Do you think that like just a language model trained on text alone is going to be able to pick up all of these different common sense facts, or do you think we need to have some way to ground these models in other modalities or experiences for them to properly learn this?
Yeah, that's a great question. I know GPT-3 is doing extremely well on few shot learning, which means especially on common sense actually. If you give it a few common sense examples, it can capture a lot of stuff. But I do think that being said, it's captured a lot of knowledge probably already. I myself haven't played GPT-3 a lot, but that's what I've heard. But apart from that, I think that we still need different modalities to capture the physical aspect of this common sense knowledge. And also for rare things that people rarely mention in their text, like rabbit is a mammal, you would probably never see that in your text.
Sure.
So those kind of things still needs to be either injected or like learn it from a different source, I think.
Great. Okay, now we have more questions. Is the shared info or a common ground between a speaker, like two speakers in a conversation, is that counted as common sense?
I think it's like, it's hard to say. It depends on how do you want to categorize this paper or something. But in my shallow understanding, I think that's more like a context, right? A shared, okay, there are two things. Shared background saying the common thing you are having, like for example, it's raining outside. One person said it's raining outside, and the other person said, oh, take your umbrella. There are a lot of shared things here. You are assuming when it's raining, you need the umbrella, and you need the umbrella to keep you from getting wet. So that's one shared information that I would definitely consider that as a common sense knowledge. But there are also more specific domain share stuff. Like in this course, we almost know like what the encoder is, what LSTM is. I would not consider that as common sense knowledge.
Right.
And back to our definition before, it must be commonly known to nearly all humans.
Great. Another question, how was the generative task evaluated?
They're our Protoqa data set. Great. So the model is supposed to give to generate a ranked list of answers. Then we match this answer string to the ground truth. And then each answer string will get mapped to what we call answer cluster, where the answer cluster contains all different surface forms of this one concept, like shower. There are different ways of saying that. Take a shower, take a bath, they're all called shower. So in this answer cluster, we have all those different expressions to say this. So we first match this answer string to the answer cluster. Then we compute like a reward matrix, as you can see here. The reward matrix gives you a reward of like according to how big the size of the cluster is, because that represents how many people is answering the question with this answer. We want to reward that fact. And after we have this reward matrix, we do a matching to actually assigning one answer string to a cluster. We get a point. And then we calculate the two metrics here. One is max answer. You can only give me 10 answers. And then what's your performance over there? And also there is max incorrect, because you can give me infinite number of answers, but after you get 3 of them wrong, that's max answer at 3. So we consider 2 type of evaluation metric here.
Okay, great. I don't see any more questions. So yeah, thanks, Lorraine. And for all the students, again, if you want to, oh, sorry, there are more questions. Oh, let me just ask those before concluding. So, oh, I forgot to ask this one. I meant to ask it at the end. For your box embedding research, did you start this direction with a particular use case in mind? Can you share it if yes?
I think the general answer is yes, because as you can see, we derive from a common embedding, and which is generally used for representing hierarchical relations. So yeah, we targeted on hypernames or entailment tasks.
Great. And another question, more questions. Could you please explain again, maybe briefly, how the box representations are trained?
So in a 2-dimension case, you would have 2 vectors. We don't even need to make it a 2-dimension. It can be like D-dimension. You have 2 vectors representing the lower left corner and the upper right corner. You initialize them randomly, and the training goal is to give the conditional probability between 2 boxes, which means the size of the volume of the intersection box divided by the box you condition on. And after doing that, you have this box predicted conditional probability. You have that. Then in addition, you have that target conditional probability. You try to use binary cross entropy to match them and train them by gradient descent.
So this is trained in a supervised manner then, just to clarify.
Yeah, yes, correct.
Okay. And okay, fast forwarding back to this current Protoqa slide regarding the evaluation, would you say that the evaluation would give different results if you show the answers to humans and ask them to rate if the answers are reasonable or not, just because of the huge subjectivity involved?
Oh, that's a great question. We try to mitigate the subjectivity by asking the answer to 100 people. And we think getting a large pool of samples definitely reduce it. That's I think based on our collection, people would, because it's not one single people's answer.
Got it. Okay, so yeah, let's stop here. Again, if you have feedback or comments or anything, or praise even for Lorraine, please do send it along on the feedback forum and get your extra credit. This is also the last lecture of the semester, so thanks everyone for sitting through these videos and asking questions. And yeah, I think, it's been a good semester, so hope you learned something at least about NLP.